Now we get into one of my personal favorite portions of this course, different types of experimental designs. There are many methods by which we can establish good experimental control and determine whether there are functional relations between DVs and IVs. Recall from last week that in single subject research, each participant or client serves as their own control condition. We don't use group designs in which participants in one experimental group are compared to other participants in a control group. Group designs average across individuals, telling us, in an extremely simplified summary, that a certain number of people in the experimental group had a reaction significantly different than the people in their control group when they were exposed to the experimental procedures. The results in this sample are then generalized to the larger population. This does not tell us the likelihood of any given specific individual having that reaction. So instead, we work to determine whether a given intervention is helpful for our individual client. When working with each individual client or participant, whether in research or in practice, we must use an experimental design to help ensure that any effect on the dependent variable was actually due to the manipulation of the independent variable. But what else might it be due to? If the dependent variable changes and we're not sure that it was because of the independent variable, what do we call one of those other types of variables? Extraneous or confounding variables, which we will discuss in more detail in a later module. For now, suffice it to say that the environment changes all the time, regardless of how we're deliberately manipulating it. There's always a chance that those extraneous changes could affect the dependent variable instead of or in addition to our independent variable. Let's start out with a review of baseline logic. This refers to how we use each type of experimental design to judge whether there was a functional relation between the independent variable and the dependent variable. Prediction means that, based on performance during the current phase of the experiment or intervention, if the independent variable is not functionally related to the dependent variable, we would predict no change in the performance. If we do see a change in performance, we must demonstrate that the change was not coincidental via verification. Verification includes return to baseline procedures. If performance is then similar to our original assessment, we verify that it likely would have maintained at that level in the absence of the independent variable. Then, replication. If we're being thoroughly skeptical, we must acknowledge that an extraneous variable could have coincidentally co-varied with the independent variable. Maybe that produced the effects on the dependent variable, and our independent variable has no functional effect. How can we provide evidence otherwise? We must replicate our experimental procedures with multiple instances of moving between phases. If we see the same effects, this reduces the likelihood that those effects were due to a variable other than the independent variable. Here are some baseline data. If our intervention has no effect or nothing changes, how would you predict that behavior would occur in subsequent sessions? The blue data series represents how we would have predicted behavior would occur in the absence of the independent variable having a functional effect. Instead, the level decreased when we changed the environment, as represented by the black data series. Now, it's possible that the change in responding was due to some other variable, not our independent variable. With that being the case, we have to verify that the previous baseline performance would continue to occur in the absence of our independent variable. When we change phases and remove our independent variable, returning to baseline, the performance did indeed change back to the level we observed previously. This is a demonstration of verification. Finally, replication. We've replicated our phase change from baseline back to intervention and have also replicated the change in performance, providing good evidence for a functional relation. Note that we want to see both replication within each phase, that is steady state responding, and replication across phases, that is change in level, trend, or variability when the independent variable is manipulated. Note that the change in the dependent variable between phases will not always be so clear. We have better evidence of a functional relation between the IV and the DV if we see a change immediately following the manipulation, and if the magnitude of the change in the level, trend, or variability is visually significant. If the data series in different phases overlap in some way, the effect is not very significant. Now we'll briefly talk about some pre-experimental designs that don't fulfill our needs for prediction, verification, and replication. Case studies have no baseline phase. Treatment is introduced prior to or in conjunction with initial observation of the target behavior. Using the experimental design nomenclature, these designs are B only, meaning that they're only the application of the treatment. There's no comparison between environmental manipulations, no replication or verification. So, you cannot demonstrate experimental control with these designs. We review the concept of a case study primarily so that you can avoid its use in research and practice. Baseline data collection is extremely important. It's the only way to determine whether your intervention had any effect at all. A-B designs have only two phases, baseline and treatment. In this case, we can predict change from one baseline phase to intervention, but there's no opportunity for verification or replication across phases. Because of this, any change in the dependent variable could have been coincidental. An extraneous variable could have occurred at or about the same time by chance alone. We have no way of knowing. These are common in applied work. It's far preferable to have more thorough evidence of the effectiveness of your intervention, such that you can strongly argue that it was your procedures that produced the change in behavior and not something else like a medication change, another new type of therapy, or the passage of time alone. However, for example, when you've already demonstrated the effectiveness of a specific intervention with the behavior of a specific client, you could use an A-B design when intervening on that client's other behaviors that serve the same function. It's a shortcut, and one that you don't want to overuse, but it's certainly better than a case study. This graph represents data collected in an A-B design. Baseline, A, is followed by treatment, B. Again, this is superior to a case study design since it provides baseline data to compare with treatment data. However, changes can't be convincingly tied to the independent variable since there's no replication of phases. Now we'll begin to talk about reversal designs, commonly considered to be the strongest of the single subject experimental designs in terms of allowing for demonstration of a functional relation. A reversal design has two or more phases, each implemented multiple times in order to allow for replication of effects. A represents the baseline phase, B represents the treatment phase. Other letters, C, D, etc., may represent additional treatment phases. The objective is to make comparisons across phases. Are there differences from phase to phase? And if there is a difference, can we attribute them to a change we made in the independent variable? When should you switch between phases? As a general rule, don't change conditions until responding is sufficiently stable over time. Stability is usually based on an experimenter's judgment, but it can be formally defined via steady-state criteria. For example, a number of sessions within a pre-specified range of the mean. These criteria must be described in objective terms and should include the limit that they're met within a reasonable period of time. Otherwise, we may simply have to accept that a behavior is very variable over time. If behavior is extremely variable during a given phase, there are likely other variables in the environment that you should be looking for to control or eliminate. You might decide these criteria based on similar criteria used by other researchers, or simply that they're being practical for the purposes of the study. Here's an example of data collected in a reversal design. An advantage of the reversal design is that it can provide a clear demonstration of a functional relation due to thorough use of baseline logic of prediction, verification, and replication. In addition, the return to baseline provides information on whether or not you need to program for maintenance of the target behavior. If the return to baseline completely removes the treatment effects, that means that you must gradually fade out your intervention and/or make sure that the natural environment is permanently changed in some way so that improvements in behavior don't disappear. Finally, the reversal design ends with a treatment condition in place. Why do you think that might be desirable? Since you end in a treatment phase, you can use that opportunity to fade the intervention gradually, or program for maintenance in some other way, such as training parents or caregivers to implement the intervention. A limitation, however, is that it cannot usefully be applied to interventions that produce irreversible effects. If I teach you to make a sandwich, it's unlikely that I'll be able to reverse things such that you 100% forget how to do so. In this case, verification and replication is not possible in a reversal design. In an applied sense, it's great that the intervention effect's maintained, but this does not allow for demonstration of a functional relation. In addition, reversal design should not be used in situations in which the intervention cannot ethically be withdrawn. In some cases, if an intervention is effective, you will not want to risk the chance that removing it will return behavior to baseline levels. For example, if you're able to eliminate self-injurious behavior, it would not be ethical to allow it to occur again just for the sake of demonstrating a functional relation. Similarly, if a behavior must be intervened upon immediately for safety concerns, you will not be able to wait for steady-state responding during the baseline phase of a reversal design. Finally, reversal designs are very time-consuming. In order to clearly demonstrate differences between phases, you must wait for steady-state responding in each phase before moving on to the next. There's no telling how long that could take, given that you need a minimum of 3 data points at a consistent level or with a consistent countertherapeutic trend. As noted in the previous point, sometimes it's simply not ethical to wait around and continue with an intervention. Each time you replicate an effect, you add inductively to evidence for the functional relation. 2 instances of each phase are generally accepted in our field, particularly if there is a clear, immediate, and significant effect. However, a repeated reversals design could be notated as A, B, A, B, A, B, etc. While repeated reversals can provide, as Cooper et al. Note, a more convincing and compelling demonstration of a functional relation, they may also begin to border on redundancy. In the top panel, data are initially trending downward, but then stabilize within the last 3 data points of baseline, around a level of 40%. During intervention, the level is lower than during baseline, with a bit of overlap in 1 data point. During the return to baseline, the level increases to a previously observed point, allowing for verification. The return to intervention does have an immediate change in level, but an upward trend such that the data overlap with baseline data. Performance levels out at about 35%, just below baseline levels with a bit of overlap. Changes in the second panel demonstrate a much clearer functional relation. Level increases from 10% to 60% immediately upon the first change from baseline to intervention. Then, level immediately drops down again with the return to baseline. The second increase in level is not as large, but there is an upward trend. The data series between baseline and intervention overlap with only 1 data point. Now let's talk briefly about non-baseline comparison conditions. In cases in which it's unethical to remove interventions entirely, you can also use different interventions as control conditions, such as non-contingent reinforcement, differential reinforcement of other behavior, etc. These procedures will be reviewed in future courses. When you're teaching a new behavior to take the place of a behavior targeted for decrease, these conditions are less likely to allow for the re-emergence of the behavior targeted for decrease, but may or may not be as effective as your intervention at maintaining the new behavior. This ultimately demonstrates that change in behavior is related to the specific procedure, not just general increase in reinforcement in the environment. Another slight variation on the generic reversal design is the multiple treatment reversal design. In this case, you alternate between baseline A with 2 or more treatments, B and C. C, D, etc. can again also represent combined interventions. What can you conclude about these data? Is independent variable 1 functionally related to the dependent variable? What about independent variable 2? Which intervention is more effective? Multiple treatment reversal designs have the same advantages of generic reversal designs and also benefit from being able to compare multiple treatments within a single experiment. Similarly, they have all the same disadvantages, but are also vulnerable to sequence effects. Sequence effects are effects on behavior in a current condition that may be affected by the participant's experience in a prior condition. This is also called carryover. Sequence effects can be addressed in part by implementing phases in a different order during each replication for each participant, and starting with a different phase across different participants. This is called counterbalancing the order of phases. However, given the need to wait for steady-state responding in each condition, the addition of more treatment phases means that this design is even more time-consuming than a typical reversal design. As you can see, These authors implemented one instance of NCR plus RC, non-contingent reinforcement plus response cost, without having an NCR phase right before it. This helped rule out the possibility that NCR plus RC was only effective if it was preceded by a period of NCR alone. We ruled out sequence effects through counterbalancing. Now we'll move on to alternating treatments designs, also called multi-element designs. It's somewhat similar to the multiple treatment reversal design in that it's used to examine the effectiveness of multiple different interventions within a single experiment. However, it's different from a reversal design because treatments are rapidly alternated rather than waiting for steady-state responding in each phase. In this graph, each data series with the data points in different shapes represents a different condition or intervention. Again, the effectiveness of one intervention is demonstrated most strongly if its data series does not overlap with the data series of any other condition. Remember, we're always looking for immediacy of change moving from one condition to another, as well as magnitude of change. Each data point provides potential for prediction, verification, and replication. In the case of prediction of future levels of responding, if performance is not a function of the changing independent variables, the data point should be similar to the one immediately prior. For verification of the relation between each independent variable and dependent variable, return from one condition to a previous one and change in behavior to a previous level at that point verifies that the independent variable and dependent variable co-varied together. Finally, replication of procedures allows demonstration of replicated effects. Each condition is implemented multiple times, at least until we see steady-state responding across each instance of that condition. You can see the key indicating what each data series represents here in the bottom right. What can you say about the different effects of the no-game condition versus the other two conditions? What about between the game and game plus conditions? We begin to see steady-state responding in the no-game condition over the last 4 data points. At that point, student 3 is consistently spelling more words correctly in the game conditions compared to the no-game condition. There does not appear to be a significant difference between the game and game plus conditions, since there is so much overlap. An alternating treatments design is in some ways superior to the multiple treatments design. For one thing, it allows greater counterbalancing to assess for sequence effects. Since conditions are rapidly alternated rather than repeatedly experienced until steady-state responding, you can have more instances of counterbalancing than you would in a reversal design. Additionally, it allows for a quicker comparison of treatment conditions, since you don't have to wait for steady-state responding. Even without steady-state, you can still compare across conditions. Other strengths include the fact that treatment withdrawal is unnecessary to see effects. You can simply alternate between multiple different treatments, not fully withdraw to baseline. It's also more useful with irreversible behaviors for this reason. We want to see if one intervention creates more change than another. Finally, intervention can begin immediately without waiting for steady-state responding during baseline. However, there are some downsides as well. Treatments should have significant differences between them for comparison. You're less likely to see differentiation between conditions since each condition is experienced so briefly before it's changed. Stimulus control may not develop quickly enough, or the participant's behavior may not experience enough exposure to reinforcement or punishment effects. Making sure that the conditions are significantly different from each other can help with this. That is, treatment conditions must be discriminable in order to see differentiation. In order to minimize treatment interference, also called carryover, the order of conditions again must be counterbalanced. Finally, if you do see differentiation between conditions, it may not be replicated in the natural environment due to the fact that rapidly alternating between treatments may be too artificial. Testing for maintenance and generalization will be very important. We'll discuss many ways in which you can adjust experimental designs to suit your needs in a later module, but to start out, here are some basic variations on the alternating treatments design. Firstly, you could begin with a baseline condition before alternating between intervention conditions. By starting with a longer baseline condition like you would in a reversal design, you could compare your intervention's effectiveness to that of the original performance. Alternately, you could alternate between a baseline or control condition along with your intervention conditions. Finally, you could end with an extended phase with the most effective intervention, allowing for gradual fading to program for maintenance and generalization. In class, we'll practice identifying different experimental designs based on the graphs, determining when to use one design over another, and how to graph data collected in different experimental designs.